Okay, so let's start talking about, we have the concepts in hand. We've, a couple lectures ago, we went through the trouble of deriving our governing equations for flow in the boundary layer. We went and simplified them down from, conventional Navier-Stokes down to equations that actually work for both momentum and for energy in a setting of a boundary layer. But remember, those were making assumptions that were based on it being a laminar boundary layer, or laminar flow in the boundary layer, where we could say, yeah, the y direction velocity, or the y velocity is very small compared to the u velocity. Well, now we are introducing this instability, and that's no longer the case. So how are these equations going to be modified to actually accommodate flow in the turbulent region? Well, we can do that. We just have to add some terms in. All right. So let's go through how to do that. If we remember here, this is where we left last time, or a couple lectures ago. So this is our continuity equation. This is our momentum equation in the x direction. Remember, y direction went away. And then this is our energy equation. So we're going to need to modify these equations to make sure that we can account for turbulence. So the general process here is called the Reynolds averaging process. And the idea is that if we were to pick, so let's just kind of sketch again our little velocity here at this location. So if we sketch this as a function of time, this is our velocity. We decided it looks something like this, where we have all this uncertainty or instability kind of happening. But on average, there's a single average value that is constant through time. So it turns out if we were to take, let's say, some time period, let's say this time period here in the red box. So let's call this, let's call this our averaging time, T int. So we're going to integrate, right? We're going to integrate over that time window. And then let's look at that time scale compared to, say, the time scale fluctuation. So if we pick out maybe peak to peak in velocity, this would be our time scale tau turbulence. So if I pick a T int that's sufficiently larger than tau turbulent and integrate that region, I should get the average value back, right? So when we're doing Reynolds averaging, what we're going to do is basically take a sufficiently long time period, but not so long that we're losing track of things that are actually changing as a function of time. Sufficiently long that we sort of mute out or average out the variability, and then develop our turbulence equations based on the averaged condition, right? So we're integrating over time, taking the average, and then the equations account for that. So, okay, we can write it out like this, where we say, here we say u bar is a function of x and y, rather than it being a function of x, y, and t, which it really is in reality. V bar is a function of x and y only, t bar is a function of x and y only. So we're integrating to get rid of the actual time variance that occurs. Okay, so let's kind of break this down a little bit. So if we decide that we want to write something for u, so we'd say u is a function of x, y, and t in reality. If I pick a location in that flow, it's going to change with x, y, and t in reality. We could decompose this down to two things. We could say, well, this is u bar as a function of x and y, u bar being the average velocity in u, plus some variability. So we'll call that u prime. U prime is a function of x, y, and t. Okay, and if I go over here and plot this out again, it's going to look something like, see, this being our velocity, and this being time. We would see, I could break this out into what? I could make u bar up here. So this would be u bar, this is my average velocity. And then oscillating around 0 is going to be my random behavior, right? My random oscillations. So down here, this is going to be u prime. Right, and you kind of see how that works. We're taking the average and then adding to that the oscillation around 0. So add those things back together and you get the original signal or the original velocity profile. Right, so we do that same thing for V. So V x y t is equal to V bar x y plus V prime x y t. And for temperature as well. So T x y t is equal to T bar. Right? I don't have to write it out, but you get the idea. So it's the same thing for temperature. And actually, think about that a little bit on the temperature side. So why would temperature be fluctuating? Well, if we're transferring heat from the surface up to the flow, there is a temperature gradient between those two positions. So if I get bulk fluid motion happening in the y direction, I'm essentially taking, let's say, a hot piece of fluid and moving it vertically in the y direction suddenly. And that, hot fluid moving vertically is going to cause that fluctuation in temperature at that position. Okay, so the process then is, let's take these and integrate them. So we're going to integrate for u. So we'll say u bar at x and y is equal to 1 over t int, right? That's the time period of integration from 0 to t int of u x y t dt. We do the same thing for v bar and the same thing for t bar, right? So we're just using this integral to sort of smooth things out. All right, that's a really quick introduction to this. We'll pick it up next time and get into more detail on it. Thanks.